Now we will see the meshing. So our geometry is done. So we can go to the next stage, that is meshing. So go to meshing. So here in the mesh module, we will mesh this 2D tube. First of all, we will map the face and then we will mesh accordingly. So if you go to here, mesh control, mapped face mesh, so select mapped face mesh and it will ask you to select the geometry. So select the geometry and apply. Now here we will mesh it according to some specific numbers. So select this edge and select the sizing. So select this edge and this edge. So we have selected to edge and apply. So to edge, we will use number of division. So number of division, how many number of nodes we need along the vertical direction. So in the tube or internal flow, the flow variables like velocity, pressure, it varies along the normal direction to the wall. So we will keep maximum number of mesh or nodes along this vertical line. So let's say first of all we will divide 100 nodes, and in the bias setting we will change it this means we will see the smallest nodes in both wall and largest node at the middle. You can keep your nodes at the same size, or you can increase or decrease the mesh size along the wall. It depends on you. Now select another sizing and select this to wall, apply, and we want to divide this horizontal line into 1000 nodes. So now update. So now you can see the mesh here. As you can see, close to the wall the mesh is much higher, and when it goes at the middle the mesh density is lower. So you can change the density if you change the bias setup. Let's say from 20 you want 50, so it's more dense at the wall and less dense at the middle. So then update, and it will show you the type of mesh at the middle and in near the wall. So in general we keep maximum number of nodes close to the wall so that we can see the boundary layer more easily, and we can resolve the change of velocity, pressure and temperature more easily. So you can play with this bias setup and number of mesh to see the changes. So let's say we want the bias setup 10 and update. We will see the change. Now you can see the change. The mesh density is high in the wall, near the wall, and low at the middle. Now the mesh is almost done. We can see the number of elements here in the statics. Go here, you can see the nodes 100,000 and the elements also 100,000. As this is a 2D mesh, that's why the number of nodes and number of elements are same. Now we need to define the inlet and the outlet. So select this wall and create name section, name it inlet, and select this line and name it outlet. Select this to wall and name it wall, and update for the last time. So now your mesh is ready for the next step, that is the case setup. So you can also play with different tools to change the mesh size, but if you really want to resolve the boundary layers, you need a very high dense mesh close to wall. That's why I choose 2D simulation first, because in 2D you can use many nodes to resolve the boundary layers first. So let's see with the 2D mesh, and then we will see the 3D mesh also. So your mesh is ready for our simulation. So we will do the case setup in the next part. Thank you. So our mesh is done, and now we will go in the next step, that is the case setup. So go to case setup and your Fluent will open. So our simulation is right now 2D, and select OK. Then the Fluent will start. So when your Fluent will load your mesh, your first job is to check your case and check the volume. Your minimum volume is positive, so you don't have any problem with your geometry. And check the report quality. So here the orthogonal quality right now is 0.99, which indicates that the orthogonal quality close to 0 corresponds low quality and close to 1 corresponds very high quality mesh. Right now our orthogonal quality is 0.99. That means our mesh is a very refined and very high quality mesh. You can see the mesh is very good. Now we will set up the case for this. If you see the problem setup here, we have the inlet and our working fluid is water. The inlet temperature of the water is 80 degrees C. This is our outlet, and our wall temperature is 25 degrees C. For the velocity, we have a Reynolds number of 500, and if you put the Reynolds number 500 here and the viscosity and the density according to the property of water, then you will get the velocity like 0.0197 meter per second for Reynolds number 500. As we are doing laminar flow problem, so for laminar flow the Reynolds number less than 1800 is considered as laminar flow. So we will consider Reynolds number 500 to model the laminar flow inside the tube. So go here, and the solver type is pressure based. We will do steady state problem, and the velocity formulation is absolute because we don't have any moving parts inside our domain. So the velocity is absolute, and it's a 2D planar problem. So if you go to model, you turn on the energy equation because we have different temperature in wall and the liquid. Select OK. In the viscous model, the laminar problem is selected, so select laminar. OK. We don't have any multi-phase flow, we don't have any radiation, changer problem, no combustion. So all of the models are right now turned off. Only the energy equation and the transport equation, that is laminar flow problem, is selected. So now go to material. In fluid you have air, so we need to change this air to water. So click here, create and edit, go to Fluent database. At the bottom you have the water liquid, so select this. You have the properties, you can change these properties or you can keep these properties as it is. Copy and create. Now you can see here you have water, liquid and air. So if you want to delete this air, select this air and delete. It will not delete. There is an error message. The error message is delete material is still in use by surface body. That means this domain right now is acting like air. So you need to change this domain from air to water. So how you gonna do that? Go to cell zone condition. Here you have the zone, surface body, type fluid. If you go to edit option, there you can see the material name is right now air. So from air you can change it to liquid water. Select this. OK. Now if you go to material and select air and delete, then it will delete. So make sure that your domain is the correct material. So select liquid water. Cell zone condition is also liquid water. Now the boundary condition. This is very important. So according to our problem, the inlet velocity is 0.0197 meter per second and the temperature is 80 degrees C or 353 degree Kelvin. Outlet is outflow and the wall temperature is 25 degrees C. So we will put these boundary conditions. So go to Fluent, go to inlet, edit. Now it will ask you the inlet velocity, that is 0.0197 meter per second. Check this unit. Our initial gauge pressure is 0 and the reference frame is absolute and the velocity specification method is magnitude normal to the boundary. In the thermal tab we have the temperature of the water and that is 353 Kelvin. We don't have any radiation, no combustion, no multiphase, so all of these tabs are inactive. So select OK. Now outlet, the type of the outlet right now is pressure outlet, so we will change it from pressure outlet to outflow. Yes, and it will ask you the weighting. This weighting is 1 because there is a 1 outlet, so OK. And 100% liquid will come from the inlet, will go through the outlet, so that 1 means 100%. Now the wall. In the wall you have no slip boundary condition for the momentum. For thermal you have a fixed temperature. You can model also heat flux. If you have a heater, you can model that with the heat flux and you can put the heat flux value. In our problem we have a constant temperature, so select the temperature and it will ask you the temperature. The wall temperature is 25 degrees C, that means 298 degree Kelvin, and that's it. No radiation, no combustion, no multiphase flow, so select OK. So your boundary condition is done. We don't have any moving part, So our dynamic mesh is inactive. Our reference value, you can check the reference value, compute from inlet. If you put here, then you will see the values, the density of water, the temperature of the water, the velocity, the viscosity, and the specific ratio of specific heat. Now the solution methods. We will use simple solution scheme. For discretization, for gradient, we will use least square cell based discretization method. For pressure, we will use standard discretization. For momentum, we will use second order upwind, and for energy, we will also use second order upwind. It will take more time, but it will give you more precise results. That's why we use second order upwind method. Now solution control, you can see the relaxation factors. Here we have the pressure and momentum. All other things are fixed. We can change this, but if you don't know the behavior of the solution, then don't change it for the first time. If you see the solution is converging too fast or too slow, you can change this relaxation factor. Now the monitor option, you can see the progress of your solution, and you can also fix the convergence criteria. Right now is 10 to the power minus 3. So you can increase or decrease according to your problem. We will see both in printed and plot form. So select OK. Solution initialization. We will use hybrid initialization. So select hybrid and initialize, and it will initialize. And then go to calculation and calculate, let's say 100 times. So calculate, and it will start calculating. So here you can see 4 lines. The white one is our continuity. The red and green one is our x and y velocity respectively, and the blue one is our energy. So every variables are reducing, which is a good sign, that is the solution is converging. So if you see this behavior, that means you have a correct case setup and your solution is converging. So it will iterate. Right now we have 100,000 mesh elements, and here the solution converged. So we will see the solutions, and we will post process some of the solutions in the next tutorial. Thank you.